Hello class, we want to continue with our studies on kinetic energy and velocities of gases. This time let's look at mean free path. Molecules in a gas travel in straight line until they collide with another molecule. Collide with another molecule or the container. The average distance a molecule travels between collision is called the mean free path. So that's the average distance one molecule travels between collision is called the mean free path. So we can see here, we want to look at the average distance between collision is the mean free path. Look at the gas particles moving around. Say, we can look at look at the distance from here to here. So that's what we are talking about. So mean free path decreases as the pressure increases. As the pressure increases, the molecules come together. They're not far apart again. So the mean free path decreases as the pressure increases. So we'll talk about diffusion and effusion. What's the difference? Diffusion, a gas molecule spread out from high concentration to low concentration. That's diffusion. When a gas molecule spread out, move from an area of high concentration of the gas to an area of low concentration, that's diffusion. But effusion, gas molecules escape through a small hole into a vacuum. That's effusion. The gas molecule escape through a small hole into a vacuum. Look at this hole. So the gas molecules are escaping through a small hole into a vacuum. This is a vacuum. Gram's law of effusion. For two gases A and B at the same temperature, the ratio of their rates of effusion is given by the following equation. So rate of gas A over rate of gas B equals to square root of molar mass of gas B all over molar mass of gas A. So you see, the rate of A is up, but in the square root, the rate of the molar mass of A is down. So I want you to just take note of that. So let's do some calculation. Calculate the mass of a gas that effuses at 4.6 times that of nitrogen. So this is the rate of the unknown gas, and this is the rate of nitrogen. So it's 0.461. You can divide it over 1. So when the rate of nitrogen is 1, that of the unknown gas is 0.461. So we want to calculate the molar mass of that unknown gas. So this is our equation. This is the molar mass of nitrogen. We need the molar mass of the unknown gas. So nitrogen, the molar mass is this. So we are using this equation. So we are going to substitute. So rearrange the equation. That's what you're going to get. So molar mass of unknown gas, molar mass of nitrogen over the rate. This rate is 0.46 squared. So how did they get this this thing squared? So in order to solve this, we want to remove the square root. So we want to remove the square root from here. So what we'll do, we'll square this and square this. So when we do that, the square root will come out of this part, but this will be squared. So that's why we have the square root, this square here. So this squared is just this squared. So if you square this, so this is 1 squared, this squared, so just this squared. So when we do this calculation, the molar mass of the unknown gas is 131 grams per mole. So calculate the ratio of the rate of effusion for oxygen to hydrogen. So we want this rate. We're going to use our equation. So if oxygen is up, hydrogen, its molar mass has to be down. So we want to calculate the ratio of the rate of effusion for oxygen to hydrogen. So the molar mass of oxygen is 32 grams per mole, and that of hydrogen is 2.016 grams per mole. And this is the rate of oxygen to that of hydrogen. So this is our equation that we're going to use. So when we solve this problem, our answer is 0.25. That's the answer. So this means that on average, the oxygen molecules are traveling at 1/4 the speed of hydrogen molecules, which is what we are expecting because hydrogen is lighter than oxygen. Now let's compare ideal versus real gas. Ideal gas laws assume that there is no attraction between gas molecules. And the gas molecules do not take up space based on kinetic molecular theory. So that is what ideal gas is saying, is assuming that the gas molecules do not have attraction between themselves and the gas molecules do not take up any space. But at low temperature and high pressures, this assumption is not valid. It's not valid. At low temperatures and high pressures, a gas behaves differently from an ideal gas and is then called a real gas or real gases. Is then called real gases. So we can see the molar volume. This is the ideal gas. This is ideal gas. Assume that all gases have this volume, this molar volume. But in reality, look at the molar volumes of different gases. Chlorine, carbon, nitrogen, ammonia, nitrogen, helium. They are different. They're different. They're different. The molar volumes are different. So the behavior of a real gas based on real molecule, because real molecules take up space, the molar volume of a real gas is larger than predicted by the ideal gas law at high pressures. So non-ideal behavior, the effect of particle and volume. So you see, this is ideal, but for argon, the non-ideal behavior, look at it, is slightly different. Let's look at the effect of molecular volume. So because real gases behave slightly different from ideal gases, van der Waals came up with an expression of how real gases will behave. So he said, at high pressures, the amount of space occupied by molecules is a significant amount of the total volume. Unlike ideal, it says the volume occupied by gases is insignificant, but in real world, it's significant. So the molecular volume makes the real volume larger than the ideal law would predict. So van der Waals modified the ideal gas equation to account for the molecular volume. So B is called a van der Waals constant and is different for every gas because their molecules are different in size. So this is the constant, van der Waals constant, to account for the volume for the real gas. And at low temperatures, the attraction between molecules is significant also. So the intermolecular attraction caused the real pressure to be less than the ideal gas law would predict. So he came up with another constant. So van der Waals modified the ideal gas equation to account for the intermolecular attraction. And the constant he used to correct that is A. It's another van der Waals constant. And it's different for every gas because their molecules have different strengths of attraction. So this is the correction for P. So in summary, the van der Waals equation that accounts for the real volume and gas is as follows. So combining the equations to account for molecular volume and intermolecular attraction, we get the following equation, which is used for real gases. P plus A n over V squared times V minus NV equals to nRT. So we want to thank you. On that note, we've come to the end of chapter 5. So please go to the back of your book, do the questions, study the questions. Odd number questions have answers at the back of the book, but even number questions don't have. Thank you so much.